Professor Ho, first of all, congratulations on winning the 21st Nagoya Medal of Organic Chemistry.
Thank you very much.
Yes.
It is really a great honor for me to receive this prestigious award.
I'm really happy to hear that.
Thank you very much.
So taking this opportunity, we would like to do some interview for questions that some young scientists might want to know. Thank you very much.
It's my pleasure.
Yes. So first of all, let me tell you about what is your goal in chemistry.
That's a very important but and a difficult question to answer. Scientific research is something like an adventure, and so it's almost limitless or endless. When you solve an old problem, then you always find something new you have to do. But I think as a synthetic organic chemist, so to me, I think to make breaking and making chemical bonds, as we want, is very important. So if we can do chemical transformation this way, we can solve a lot of problems, and the chemical synthesis will be very easier. Just to break and make any chemical bonds at will.
That will be extremely challenging.
Yes.
But it's very nice goal to have.
Yes.
I agree. Yeah.
Right.
Thank you very much. So when you design new catalysts or reaction, what do you have in your mind?
I think the originality and the uniqueness is very important to us, and we always think about how to achieve something that cannot be done previously or by other means, and by use of our catalyst and all reactions.
So in your research, what was the critical moment, or what were critical moments, do you think? And when was that?
Well, I think, and our discovery that the cationic half sandwich rare alkyls serving as a can serve as a catalyst or unique catalyst for the polymerization and other transformations is quite and critical in my research. And we found that previously, and the people, including me, and believe that the neutral rares and alkyl compounds do not require a co-catalyst or do not change to the cationic species to show high activity for the polymerization of olefins. And we found that the cationic species of rare complexes can do much better, something very unique in olefin polymerization and in the other chemical transformations. And based due to this, in the course of this research, and we also found that transformation of half sandwich dialkyl compounds to hydrides could generate a new family of very unique hydride clusters, which can show unique and the properties and the reactivity. And this later on has led to the discovery of the dinergen activation and benzene ring breaking, and by using the titanium hydride clusters.
So I think it's from myself, it's really interesting kind of history of research. So you were initially thinking about how the complex reactivity,
Yes.
or how it behaves in the polymerization,
Right.
but it found some key aspects.
Yes.
And then that was translated to even more small molecule activations.
Yes. Yeah.
So from like a polymer, the benzene.
Yeah.
But it's all connected. in your
Yes,
mind,
right.
Right?
Right.
Yeah. It's
Yeah.
very interesting. Yeah.
I think it's quite important. When you see something unusual, something you have not predicted.
Exactly.
Yeah, and then you need to think about how and why and how to and in some cases I also often receive reports from students and postdocs about the decomposition of organometallic compounds. As you know, organometallic compounds, especially the rares and compounds, are very sensitive to the air, to moisture, and in some cases, in many cases, we see decomposition by moisture, by air. But in some cases, it's not the decomposition. It's the true reaction, a very interesting reaction with some organic substrate, and just as we did in the discovery of the dielectric activation, we wanted to do hydrogenolysis of titanium alkyl compounds to make the corresponding titanium hydrides in the half sandwich titanium alkyl compounds, and in the presence of dinitrogen, because we do this reaction, and in a glove box filled with dinitrogen, and but serendipitously we found the dinitrogen was activated and hydrogenated and incorporated into the hydride cluster. And at the beginning, we thought, well, this decomposition, okay, because we did not see any evidence of pure titanium hydrides. And after careful examination of the products, we found it is the activation and the hydrogenation of the dinitrogen.
It's very interesting.
And the benzene breaking, and it's also we did the recrystallization and of the titanium hydride compound in benzene. As you know, benzene is a good solvent for, and it is non-reactive compound and solvent. I'm sorry. We use benzene as a solvent, and to take an MR spectrum and to carry out reaction. But surprisingly to us, and the benzene ring was broken by the hydride, and even in the room temperature.
That's, I think, really amazing. So if you didn't use benzene as a solvent, you're not going to discover that. Or if your glow box were filled with argon instead of nitrogen, you're not going to discover that.
Right.
But this is very, very interesting.
Yeah. I think the serendipity is quite important.
So if there's a kind of message to young scientists, maybe that don't miss, something that it's really curious things.
Right. So I think the chance is there in everywhere. So we need to keep alert, to the new phenomena.
So Professor Ho, so what do you think is the biggest barrier when you try to solve problems related with sustainable energies and resources?
I think that's also a very important but difficult question. I think to solve the problems related to sustainable energy and resources, and there are a lot of issues we need to face. First, I think in the market problem, the cost problem, and to us, as scientists, I think the further scientific breakthroughs are very important. So I think, there are a lot of issues related to politics, economy, and also science. We need to do more, and to make further scientific breakthrough.
So Professor Ho, what future do you see in synthetic chemistry? Let's say 20 years.
I think synthetic chemistry will become more and more important in the future in relation to material science and chemical biology and plant science. We use the synthetic chemistry as a tool to understand the life and some, and other many important issues. As to the synthetic chemistry itself, I think, for example, efficient use of what we thought some, inert or inactive chemical bonds to the efficient chemical synthesis, and it's also a very challenging problem. And to synthetic chemistry, for example, further efficient or particular use of CH bond, CC bond, and enantiomer selective transformation or functionalization of CH bond and CC bond, just as some examples. And also, I think the conception and in your in the center and also in our center, I think the fusion, okay, of synthetic chemistry and with other fields could be a very important direction.
I think that's very important. Yes, I agree. Yeah. So maybe synthetic chemistry can be used for like a problem solving.
Yes.
You know, interdisciplinary research.
Yes.
It's critically important because if there's no molecule, we can't do anything.
Yeah. Yeah. And at the same time, also, we still, there are a lot of challenges to synthetic chemistry itself. For example, as I mentioned, we still don't know how to break, and see, we still, have problem to selectively break, for example, CH bond in the complicated compound, CC bond, for example. And if we can achieve, selectively break and make any chemical bonds as we want, that would be great. It's not only, important for the synthetic chemistry, but also, for the development of other fields, I think.
So Professor Ho, finally, what is your next challenges in your research?
Well, that's also a difficult question. As mentioned, I think the scientific research is almost endless, limitless. I think, and we would like to achieve and efficient and catalytic and synthesis of ammonia from dinitrogen and milder and conditions based on what we have discovered recently. At the same time, we would also like to see if we can and achieve efficient and catalytic transformation of CC bond of aromatic compounds, and to find some new opportunities for the efficient use in the transformation of inactive aromatic skeleton.
Wow.
And meanwhile, we are also trying to make new functional polymer materials with new structures, new compositions, and
the inert bond activation toward small molecule synthesis toward polymer, and then make many things possible that was not possible previously.
Yes.
Yeah. So finally, can we have a message to the young scientist?
Be unique and do what you really want to do, but do not confine yourself to a narrow field.
Thank you very much.
Thank you. It's my great pleasure.